we have been talking about what happens to these high mass stars at the end of their lifetime. And at the end, we discussed that after going through these different fusion reactions, and after this process called photo disintegration, the star have a neutron degenerate pressure at the center. And as a result of that, there will be a type 2 supernova explosion. And after the supernova explosion, this dense core at the center will remain there, right? Now, this dense core consists of neutrons. So all you have is neutrons at the center of this core. And because of the neutron, there will be a neutron degenerate pressure, right? Now, this continuous effect from the gravitation, which always try to collapse the star towards the center, will be stopped by the neutron degenerate pressure. And because of that, you will have a neutron star at the end, right? Now, this neutron star is connected to this new type of object called pulsars. So the pulsars means basically a rotating neutron star, and we remember that we discussed this last Friday, that when a neutron star rotates around its own axis, sometimes its magnetic field aligns towards the Earth, and when charged particles accelerate in this magnetic field, you will get these pulsars, right? So if you detect a pulsar, that means there will be a neutron star in that particular location, right? And at the same time, we discussed that converse is not true, which means there may be neutron stars that do not have this effect pulsars, right? So there are two different things, right? And so all neutron stars may not be pulsars, but all pulsars should be neutron stars, right? And this is where we stopped last time. And then right, so just give me a minute. I just may have opened up a presentation. Just give me a minute. So I assume that you can see the presentation now. So if you cannot see, then please let me know, right? So we talked about neutron stars, and today we will talk about gamma ray bursts, a different phenomena, which is actually not directly related to what we have been talking, but this is something new that probably will be better if you have a bit of understanding about gamma ray bursts as well. Now, these the gamma ray is, it's a high energy ray in our electromagnetic spectrum, as you know. Now, these gamma rays were actually discovered accidentally by a series of satellites launched by the US Defense Department, right? And this actually came as an accident because they didn't plan to detect gamma rays in the sky, but what they have planned is to detect different nuclear experiments or reactions, or maybe nuclear tests that are done by different countries in the world, because they have this kind of an agreement, and they wanted to monitor these different nuclear activities which are carried by other countries. Now, the reason that they used a gamma ray detector for this one is, if you have nuclear type of reactions or activities, they produce these high energies, which you can easily detect from gamma ray detectors. So what they have done is they send a series of satellites to the sky to detect those kind of activities through gamma ray detectors. But surprisingly, they have not detected anything like that on the ground. Instead, they had recorded some of the gamma ray bursts that came from the sky from different locations. Right, so they did not expect this one, and this is an accidental discovery. For that reason, so nobody knew at that time what these gamma rays are and how far away these sources, right? Where these gamma rays comes from, and then this NASA launched a different observatory called Compton Gamma Ray Observatory in 1991 to specifically look at these bursts, and then after that, astronomers began to identify a lot of these kind of bursts, right? Now, the map that you see here on the right-hand side, now on the left-hand side is how it looks like, this Compton Gamma Ray Observatory. And then on the left-hand side is the map of gamma ray burst positions measured by this Compton Gamma Ray Observatory. And something interesting to see here is the map is isotropic, right? Which means same in all directions, which means that there is no specific direction that we receive gamma ray bursts. Instead, the gamma ray bursts are recorded in all the directions in the sky, right? And also you can see that these different colors, the colors are for actually the total energy in the burst. Right. Now, even though we have detected these gamma ray bursts at that time, we did not know where the sources are, right? Only thing that we can see is the sources seems to be distributed isotropically. So which means they could appear anywhere in the sky with no preference region over another. And this concept about the isotropic and homogeneous universe, we will also talk about that when we start talking about general theory of relativity, probably in the next week. And the other thing is there is no second burst come from the same location, right? So you have only one burst, one gamma ray burst from one location. And the problem with these early gamma ray telescopes is they didn't have sufficient resolution to pinpoint the exact place on the sky, right? Instead of, they just had an area. Okay, this area is where the gamma ray burst may have emerged. And as a solution for that, this second satellite called VIPOSAX is launched in 1996 to locate these positions more accurately. So what that means is within a few arc minutes accuracy. So still it is not a pinpoint accuracy, but they can narrow down the location. And this satellite observed one burst came from the constellation Orion, and all of you know about this Orion constellation, right? Now, after they located this particular burst around the constellation Orion, they used the other telescopes to observe the same location, and what they have found is this slowly fading X-ray after this gamma ray burst, right? And then this is actually recorded as the first successful detection of an afterglow from a gamma ray burst. So what that means is you locate a gamma ray burst, and after that you use a different telescope to look at that particular position to see what is there. Right? So if you see some light there, so that is what you call as the afterglow, right? That is what is remaining after the gamma ray burst. And in the same night, This William Herschel telescope, which is a 4.2-meter telescope in Canary Islands, also found a fading visible light source at the same position. Right? So there is something there. So that is the idea. When this gamma ray burst came, there is always something in that particular position. Now, so what they have identified is this fading point of light is a very distant galaxy. So the conclusion is that these gamma ray bursts are coming from some kind of galaxies in different parts of the universe. Right? Now, something to add here, when in this particular gamma ray burst, you can see that when they detect something, they look at the same thing from the other telescopes, right? So this is frequently used in astronomy nowadays. Now, for example, this new telescope called LSST, or Rubin Observatory, which should be start its operation by end of this year or early next year, which is a huge telescope and is capable of scan the whole, southern hemisphere within a few nights, and it is one of the leading telescopes that has planned to operate within the next decade or so. So what it does is it has this algorithm that it can detect an asteroid or transient planet or anything like that automatically, and then it can ask for other telescopes to look at the same position to get more details, these kind of things, right? Now, same thing happens for this when scientists detected these gravitational waves from colliding black holes a few years ago. So what they did was, once they detected a sign of a gravitational wave, so they used to ask for other, optical telescopes, leading optical telescopes at different locations to point at that particular location to see what they can see there, right? Those kind of things. So normally it's a, kind of a network that operate within the astronomy community, right? Now here is an example for the gamma ray burst that was detected in 1997. And these are false color images, by the way. And this image in the left-hand side, and you can see a place that you had a gamma ray burst, and the right-hand side, the same thing is enlarged. Right here, this region right here is the enlarged version of this same location right here. And the gamma ray burst, the source is right here, and this is the host galaxy, right? Now, what you can notice here is this large white circle is the host galaxy, the galaxy where you had this gamma ray burst, and here is the exact location where the gamma ray source is. And you can see that the source is not exactly at the center of the galaxy, right? It's kind of, a little bit towards one side. And here is another gamma ray burst observed in March 2008. And this is an afterglow for one of the gamma ray bursts named in this number. And this is detected from the Swift Observatory in X-rays. And this observatory is the one that was sent after the previous observatory. And this Swift Observatory is more capable of doing things in gamma ray research compared to the other telescopes. And later, as I told you, by observation from the large telescopes, the astronomers have found that this particular burst occurred at a distance of 8 billion light years from Earth. Right? Now you can see that how far is this gamma ray burst that have occurred. Now this is why this type of gamma ray burst took the attention of astronomers, because they are very they came from very far away, which means the gamma ray bursts are, nice way of looking at the earlier universe. And now actually we know more details about these gamma ray bursts, and we have astronomers have divided the gamma ray bursts into two categories. The first one is called long duration ones, which means those type of gamma ray bursts last for more than 2 seconds, right? And maybe they can go up to about a minute. Now, what they have found is these type of long duration gamma rays have come from distant galaxies that are still actively making stars, right? And most of them are actually, making these actively making stars, which means those galaxies, inside the galaxies, they have a lot of high mass stars. Both high and low mass stars, and they are still active, which means they are making they are having these star formation activities going on, right? And we will learn a little bit more about star formation activities of different types of galaxies in the next set of lectures when we talk about galaxies. And found to be located in regions of the galaxy with strong star formation activity, such as spiral arms. Right? So they are always located in regions where you get this strong star formation activity. Now, for spiral arms, which means you will see that galaxies are mainly divided into different categories. There are two of the main categories are spiral galaxies and elliptical galaxies. These for the spiral galaxies, now for example, our own Milky Way is a spiral galaxy. The spiral galaxies have these spiral arms. Right? Now, if you look at carefully in these spiral galaxies, most of the star formation activities are actually going on in these spiral arms, right? And that's a kind of a signature for these spiral galaxies. And we have nice evidences for those. So this is why the gamma ray bursts came from these spiral arms of these spiral galaxies. And the next thing actually I was trying to tell you is these bursts have come from young and short-lived and therefore massive type stars. Right? So these bursts have come from young and short-lived stars. Right? And which means, young and short-lived stars are the stars that are in the top left corner of the main sequence of the HR diagram, right? If you remember that. And those stars are very massive and they are short-lived. Right? So these things are connected to each other. Now the other type of galaxies, other type of burst is the short duration ones, which means they don't last more than 2 seconds. So always their time will be lasting time will be less than 2 seconds, right? And typically a fraction of a second, even less than that. Now these type of short gamma ray bursts appear to be coming from merge of two compact stellar corpses, right? Now, the same thing again, but you don't have asked here the word. So what that means is it could be two neutron stars. So actually I have updated this slide after your question. And this could be two neutron stars, or maybe neutron star and a black hole, right? So which means if two neutron stars merge together, or if there is a neutron star and a black hole merged together, so these processes will be very violent, which will emit a huge amount of energy. And this may be the reason for these short duration gamma ray bursts, right? So that's what it means, right? Now, the reason actually that we are talking about these gamma ray bursts, it's a kind of a way of probing the universe, right? Now, if you look at these long duration gamma ray bursts, they are actually very bright, and because of that, they could be easily seen at in very far away distances, right, which correspond to a few hundred million years after the expansion of the universe began. Right? Now, to add something here, we believe that our universe has began 13.7, around 13.7 billion years ago. This is what we will talk in one of the lectures in under the cosmology. And these gamma ray bursts are actually go back. They are very bright. So if something happens, even at a very early universe, we should be able to see it, right? And that's the advantage. So we have observed some of these gamma ray bursts that have occurred after a few hundred million years after the Big Bang or the expansion of the universe, right? And this Big Bang we will talk separate in a separate lecture. And actually, this is the time that theorists think that the first generation of stars formed. Yeah, you have this earliest gamma rays, right? Now, so what I mean from this first generation of the stars is that there are stars that we talk under 3 generations, right? We call that those as population 1 stars, population 2 stars, and population 3 stars. And what those actually means, I will explain that in the final slide of this presentation, right? And as of now, the most distant gamma ray burst that we have found was in a galaxy with the redshift correspond to a 13.2 billion light years, right? Now, what that means is when you measure the redshift of a galaxy, you can find the distance, right? So that's how you get this age, right? And we will talk a little bit more about those things in coming lectures under Hubble law and those kind of things, right? And this means this particular gamma ray burst has happened only 600 million years after the Big Bang itself. You may feel that it's still a long time, but comparing the age of the universe, which is around 13.7 or 13.8 billion years, something that if we can see something that has happened after 600 million years, then it is a great achievement, right? Right. Now that's about gamma ray burst. So let me introduce you the final product of this stellar evolutionary process for high mass stars, which are black holes, and all of you know about black holes. What I am going to explain here is during this stellar evolutionary process, at which point that we will have a black hole, right? Now, if I go back to this stellar evolutionary process that we have taught, we have seen that these low mass stars, they end up as white dwarfs, while the other high mass stars finish their life as a neutron star, right? So those are the two endpoints. Once again, the low mass stars will become a white dwarf, and of course, white dwarf will eventually become, it is possible that the white dwarf become this type 1A supernova as a result of, creating some matter from a surrounding star. And for these high mass stars, they will undergo this type 2 supernova explosion, and after that you will have this neutron star remaining, right? So those are the two endpoints. And if you look at these neutron stars, they are actually balanced by neutron degenerate pressure, or the pressure that is created by neutrons due to these pressure created by these densely packed neutrons. And So basically this neutron degenerate pressure is the force or the pressure force created by this neutron degenerate pressure will balance the star by collapsing it. Otherwise, due to this gravity always the star tend to collapse, right? Neutron degenerate pressure holds it in neutron stars, right? But there may be stars, if the star is very huge, there may be a limit that even this neutron degenerate pressure can hold the star, right? Or prevent the star collapsing. Right? And if we have a very massive stars, specifically if you have a neutron stars that are greater than 3 solar masses, right? They cannot support themselves against gravity, because if the mass increases, then the power of gravity increases, right? And because of that, any neutron star that has a mass greater than 3 solar mass cannot support themselves against the gravity, right? Now, what happens at this particular situation is that these huge objects will overcome the pressure from their neutrons, right? And then they will start to collapse further, right? Once again, just understand that this is this is a competition between gravity and the pressure created inside the star, right? Now, gravity is always there. Gravity is always there. So it's the force, repulsive force that that comes due to the pressure at the center is what is changed right from the beginning. So when hydrogen becomes helium, and then that process happens, there is a pressure, and it will be balanced by the gravity, and then it goes on like that for different stages. Gravity is, however, always there, and there is a point for these neutron stars, especially high mass neutron stars. Even this neutron degenerate pressure cannot stop the gravity, right? So when this happens, the star will start to collapse further. The problem that now we have is there is nothing to stop gravity, right? Because it has gone to the neutron degenerate pressure as well. Right? Now, the problem is, unlike the other situations we have encountered, there is now nothing to prevent the star from collapsing in on itself. Right? So its star itself will collapse now, because there is nothing to stop the collapse of the star. Right? Now, what will happen is this squeezes all of the star's matter down into extremely tiny volume of space. This means the density will be extremely high. So I guess you can understand what happens now, right? So there is nothing at the center, so the star will continue to collapse to a very tiny volume, right? Now, the consequences are completely different at this point, because you cannot explain these things from Newton's theory now. The one consequence is that the light is unable to escape from the inner regions of the collapsing star. Now, the one consequence of this incredibly high density is that even the light cannot escape from this inner region of this collapsing star, right? And this is why we call these dense objects as black holes, right? Now, this is the endpoint of a star. Now, there are few or many unfamiliar phenomena that occur in these regions of extremely high density. And these are actually predicted by Einstein's theory of general relativity, right? Now, this is why, as the next step in next week, we will be start to learn about general theory of relativity, right? Because we cannot explain some of these things without the help of general theory of relativity, right? Now, some of the things that will happen as a result of general theory of relativity is that suppose that there is a bright object located close to a black hole, right? Now, light leaving this object will lose energy as it moves away from the black hole, and this is due to the curvature of space by the black hole. Right now, so just to introduce you brief the idea of a general relativity, what happens is when you have a huge mass, that mass can curve the space-time, right? So that's what happens. Now, if you get our own solar system, we have the sun at the center, and if you compare the masses, mass of the sun is huge compared to all the other planets. So what could happen is mass can curve the surrounding space-time, right? So that's what happens. Similarly, when you have a black hole is even a denser and massive object, even more than our own sun. So this particular object can curve the space, right? And so what will happen is the light that leaves an object will lose some energy because of this particular effect, and this is called gravitational redshift, right? And remember that what you have learned up to now from A levels up to now is called just a redshift, right? So that is called Doppler redshift. You know that happens due to the relative motion of two objects. So this gravitational redshift is a different thing, right? This happens due to this the curvature of the space-time close to a black hole, right? So now this effect called gravitational redshift. The idea is this will cause photons of light to shift longer wavelengths, right? So what happens is light photons will shift to a longer wavelengths due to this effect. Right? Now the light that is not moving directly away from the black hole will have its path curved towards the black hole, right? Now, if an object is close enough to a black hole, none of its light will be able to escape from the black hole. So which means the light that is directly moving outwards will be infinitely redshifted, which means you will never be able to catch that light, or you will never be able to detect that light because they are infinitely redshifted, right? Now, to explain that, here is kind of an example, the light parts near a massive object. And on the left-hand side is a person stand on the surface of a normal star with a flashlight, and you can see that he switch on the flashlight and light is distributed evenly towards each and every direction. And now consider that if this star collapses so that it is just a little larger than a black hole, you know, just think that this complete star will collapse to a very dense object comparable to a black hole. Then what happens is all the light except that one into the upward direction, all the light is curved back to the surface, right? You can see that in this particular image, all these light, those are curved back towards the surface. So that's what happens under gravitational redshift. So they curve back towards the surface. This is because of the curvature of the space-time, right? So you will learn this more and more when we talk about the general theory of relativity. Right, and apart from that, so this gravitational redshift is strongest very close to a black hole. You may be thinking that whether we cannot observe this gravitational redshift in our day-to-day life. The answer is it is there. It is there. The gravitational redshift is there because any mass that we have can curve the space-time. So you will have this effect. But the thing is, this effect is very, very tiny. You don't need to worry about it, right? But when you go for a thing like a black hole, then you have to think about it, right? Now, one of the nice examples of application, does anybody knows that where would you apply any of these general theory of relativity or special theory of relativity in day-to-day life? Anybody knows that? Is there any point that even we apply these things? We don't know. Is it, so does that means that for this learning all these effects in the general theory of relativity, whatever the relativity that Einstein has introduced, is only useful for talking about stars and galaxies, or whether there are other uses of that day-to-day life? Anybody knows that anywhere whether we are using it? Nobody have an idea? Right. So I guess one of the nice examples that we are using here is the UI Google Maps, right? And do you know that Google Maps won't work properly if you do not apply the curvatures of the space-time, effects of the curvatures? Because there is something called gravitational time dilation also. If we have time, if we get time, we will talk about that at the end when we talk about general theory of relativity. And when you, so the GPS normally works from the satellites that goes around, right? So what happens is, due to these masses that you have, I'm not going to talk to you in detail, but just go and search somewhere GPS and the general relativity. And if I have a document about that, I will send that to you as well. If you do not incorporate the theories of general relativity and the special relativity for the GPS calculations, your location will be off by miles for one day, right? So that is the reality. So what you don't know is that you are applying that what you are learning, right? I mean, I will send you a document to read about that time permits, but if we get time, we will actually talk about those, right? Right. So this is just an example of application of these things in your real life, and you can think that what happens if the Google map is off by few miles or like that. And how important is that in these days, right? Now, there is something called event horizon of a black hole. By the way, the gravitational redshift is strongest close to a black hole. And in fact, every black hole has a precise region within which light is unable to escape. So there is a marked, hypothetical region that if you go inside that region, even the light cannot escape, right? Because of this huge curvature of space-time. And this particular region is what we called as the event horizon, right? And the distance from the center of the black hole to its event horizon is called as the Schwarzschild radius. And this does not refer to the actual size of the black hole, and since its matter has collapsed down into the center, right? Now, this is not the size of the actual size of the black hole, but there is a radius that is measured from the center towards a particular point, which we called as the Schwarzschild radius, which we called as the event horizon. Right? Now, the importance of the event horizon is that you cannot see anything inside the event horizon because the light cannot escape from that, right? So that is the idea. Now, if you need, you can calculate the Schwarzschild radius directly because this is directly proportional to the mass of a black hole. For example, a 3 solar mass black hole has a Schwarzschild radius of about 9 kilometers. Right? So which means if you have a black hole with 3 solar mass, there will be a Schwarzschild radius of 9 kilometers, which means from the center up to a radius of 9 kilometers, you can go up to that point, but you cannot go inside that, right? Because if you go inside that radius, just cross the Schwarzschild radius, then you won't be able to come back again, right? Now, this is why this particular concept is, kind of good, popularized among, science fiction and everywhere because of these, kind of controversial, not actually controversial, completely different phenomena that you get to experience. Now, this is how you simply calculate the Schwarzschild radius. G is the gravitational constant, and m is the mass of the black hole, and c is the speed of light. Now, you can prove this equation yourself if you need. In more simple way, it will be actually, you just think about the escape velocity, right? How to write the equation for the escape velocity. You have done that, right? You know how to calculate the escape velocity for Earth. Right? You just compare the kinetic energy with the potential energy, right? So you kind of the same way you can calculate the Schwarzschild radius, assuming that the escape velocity will be the speed of light. So just think it in this way, that way, and you just write the two equations and can get easily obtain this equation. Right? Now I have two questions that I have put on here. The astronomers have traced the paths of several stars near the center of our galaxy and found that they seem to be orbiting an unseen object. And this is dubbed as Sagittarius A, with a mass of about 4 million solar masses. What is the size of its Schwarzschild radius, right? So you are given the mass as 4 million solar masses, and then you have to plug that value in this equation to find the Schwarzschild radius, right? That will give you the Schwarzschild radius, in fact, for the supermassive black hole at the center of our galaxy. And just to compare these values, so I have given a day-to-day life example, asking that you have a size of a black hole that contain only as much as mass as a typical pickup truck. That's around 3,000 kilogram, right? Think about that, a bus or truck, something like that, and you can calculate the Schwarzschild radius. And do these two calculations yourself, and you will understand the values, two values for the Schwarzschild radius, and then at the same time, you will understand why we are more concerned about these effects in space compared to our day-to-day life. Right? You will see the two values and see how negligible is this second value when you calculate it for a 3,000 kilogram. Right? And the name came from this under this name from this scientist called Karl Schwarzschild. He is the German scientist first demonstrate mathematically that the black hole is possible and to determine the size of an unrotating black hole, event horizon, right? And then there is something called Schwarzschild metric and those kind of things. We will try to talk those when we talk more about the general theory of relativity. Right, so this will summarize actually the end state of all the stars. And so here is a summary of everything what we have probably talked in last 10 lectures or so. Right? So what will happen to stars is if a star has a main sequence mass less than 8 solar masses. By the way, these question marks right here should be actually solar masses. For some reason that symbol doesn't appear here, I may make changes. This should be 8 solar masses. And the final masses will be less than 1.4 solar masses when they become a white dwarf, right? So that is the condition. So you can just clearly understand that the main sequence, when the star on the main sequence, its mass should be less than 8 solar masses. However, when it comes to the end state as a white dwarf, its mass should be less than 1.4 solar mass. And you probably should remember this. This is the Chandrasekhar limit, which means if the mass of a white dwarf is greater than 1.4 solar masses, the white dwarf will accrete matter from surrounding star and will become a nova or a supernova. I mean, not a nova, actually, it will become a type 1, a supernova, right? So that means complete explosion of this star, right? Now, if the main sequence mass is main sequence is what you have in this HR diagram, is between 8 solar masses and the 25 solar masses. Then the final mass of these type of stars will be between 1.4 and 3 solar masses, and they will become neutron stars. Right now, if a star has a main sequence mass greater than 25 solar masses, their final mass will be greater than 3 solar masses, and this is the condition to have a stellar mass black hole. Right? And the reason that you have this word right here, stellar mass black holes, because there are different other types of black holes we used to have. For example, one type is called primordial black holes that we used to assume from theories that those type of black holes may have existed from the beginning of the universe, but as far as I remember, we have not detected those yet. And because of that, we have these stellar mass black holes. What that means is these type of black holes are due to the process of this stellar evolutionary process, right? Right. Now, just to add something at the end. So everything that we have talked up to now is about more or less related to these population 1 stars, right? So there are 3 population types of stars, as I have mentioned previously. This is because we have theories to tell that the universe has began around 13.7 billion years ago. And at the initial point, we had only hydrogen and helium are the only available element. And because of that, the first stars that are born with virtually no metal content, because there was only hydrogen and helium, right? So in the first set of the stars, when they burn, they didn't have these other type of metals inside those. So basically, they only had hydrogen and helium. So those type of stars we normally call as population 3 stars. So those are the oldest type of stars of first generation. And the next generation of stars formed with extremely metal poor. Now, I guess you can understand what happens here, because when you have the first generation stars, they have only hydrogen and helium initially, but they will go through this process of evolutionary process, which will add up, make these heavy metals and everything. And when you come into the next generation stars, which means when we have the next generation stars, after these supernova explosions and everything, of course, they have more hydrogen and helium, but at the same time, they will have a small amount of metal content as well, because they are available in the interstellar medium, right? For the second generation. And those type of stars are called population 2 stars, right? And the next generation, after that, actually metal rich stars, because for the population 2 stars, then it will create more and more metals. So which means for the latest generation, you have more metals in the stars, right? So which means they are called population 1 stars. So that's how these 3 generations of stars, we categorize stars in this way normally, right? Right. So that will actually finish our story about the stellar evolutionary process. And since we have some time, I can start talking about stellar motion, which is a different section. But before I start it, anybody have any questions, feel free to ask. Right. If you do not have any questions, let me start the next section. And I was actually going to suggest you one thing, since we have only like small number of here for the Zoom session, we probably will be able to, I would like that if everyone can switch on the videos and start the lectures from the next time, right? Assuming that you are not charged for your data and your speed is good enough, right? I mean, it will be more interactive than, just talking to someone who is invisible here, right? So I can switch on my video and you can, it will be more, sometimes maybe more interactive. So let's see whether you would like to do that in the next time when we start lectures. Right? I mean, if you have signals and everything, right? So I don't know, that's up to you. That's why I cannot force you to do that. Right. So the next section is about stellar motion and binary star systems. And so I hope you can see my screen, right? So if not, please let me know. You should be able to. You should see my shared presentation now. Stellar motion and binary star systems. Right? So if you can't see it, then please let me know. Right. So in this image right here, you can see that we have Earth, we are right here, and there is a star that moves on the sky, right? Now stars actually move in a, if you look at the motion of a star, there are few, different ways that you can define it, right? Now when a star moves, actually the star is moving a direction like this. So that's the true velocity of a star. But what we are normally measuring for a star is this angular movement across the sky, right? So this is called proper motion of a sky, proper motion of a star, right? And this one right here is whether the star is moving away from us or move towards us, right? So that is called the radial velocity, right? And if we know the radial velocity of a star, now this can be measured using Doppler effect. And if we can measure the proper motion of the star and the distance to the star from Earth, then we can calculate the velocity of the star towards this direction. So that is actually not the proper motion, right? Proper motion is an angular measurement, but if we know the distance from here to here, you can calculate the velocity towards this direction, right? And if we know this velocity, which is we can call as the transverse velocity and the radial velocity, then you can calculate the resultant velocity, which is the true velocity, right? So that's how you normally calculate the velocities of stars, right? So that is, I guess I have basically mentioned you what I'm going to talk here in this particular lectures. Now, when you look at the stars up in the sky, they appears to be fixed in their relative position, right? So that is our normal, that is what you can normally observe. However, this is an illusion caused by the very large distances to stars, right? So that is not true. So what you can see is due to the fact that the huge distances that we are looking at, right? So when you, even in day-to-day life, if you look at something at a very large distance, if the movements are smaller, you cannot, detect it, right? You feel that it is at the same position. Now, the same thing applies for stars. In reality, what happens is the stars actually move with respect to each other and change their relative positions. So this is what actually happens. Now, when stars are moving, as I have shown you in this front page picture, there should be a way to measure their velocities, right? Now, one type of velocity that we can measure is the radial velocity. Radial velocity is normally measured using Doppler shifts, right? Because if a star is moving away from us, it will be redshifted, as you see here, right? If a star is not moving, if it is stationary, there will be no shift of the line. So just look at one of these lines. If it is red moving away, it will be red shifted. If it is moving towards you, then the line will be blue shifted, like that, right? Now from this, actually, you can measure the velocity, right? Now this is actually, you cannot measure the redshift and the effect of this Doppler effect across the sky, right? So what you can, where you can measure these Doppler shifts of the stars is if a star is moving away from you or move towards you, right? And that is called radial velocity, right? And this is usually measured in kilometers per second. Now, the other type of motion a star has is the proper motion, which means the movement of the star on the celestial sphere or across the sky. Now, a nice example is this particular star called Barnard star, which is actually considered as the star with the largest proper motion. And if you look at these three images, A, B, and C, you should be able to identify which star is moving here, right? You can see that this star pattern has not changed much from 1985 to 1995 to 2005, but there is a star actually that moves across this images. That is this particular star right here, right? So it is right here, and then after 10 years, it has come into this position, and after another 10 years, the star is right here. You can see, right? So the position of that particular star is changing, and this is the Barnard star, right? So that's called Barnard star. And you can see that relative to the other stars, the position is changing across the sky, right? And this type of motion is what we call as the proper motion. And the previous one that we talked is the radial motion, which you have to use Doppler shifts to measure the radial velocity and all kind of these things, right? Now these changes are actually very slow, and you can see that it is slow because after 20 years, it has gone just from here up to here, right? So very small distance, right? Even the star with largest proper motion takes 200 years to change its position in the sky by an amount equal to the width of the full moon, right? You can see that you can, you know the width of the full moon, right? If you go, so the next week you will have the Poya day. If you go outside, you can see the size of the full moon. Now, to move this star from one corner of that full moon to the other corner of the full moon, it takes 200 years. So this proper motion, you can see that it's a very small amount, right? So that's why we don't feel it that much. Right, now this is one of the constellations that we have up in the sky. This is how the constellation looked like 50,000 years ago, this particular constellation. And today, this is how it looks like, right? You can see that these arrows show up in which direction that these stars have moved. Right? And after 50,000 years from now, this is the shape of the constellation, right? Now, this happens due to the different proper motions of different stars in this constellation. You can see that the shape of the constellation Big Dipper has changed a lot, right? But the problem is this change has taken around 100,000 years. This is why you cannot see it, or you cannot observe it, or you cannot feel it, but it happens. Right. Now, combining space velocity and the proper motion, this diagram nicely explains all these type of motions together. And this is the radial velocity. And as I have mentioned before, the radial velocity may be towards to you, away from you. And because of that, using a Doppler shift, or from the Doppler effect, you can measure this radial velocity, right? All of you know that you can measure that, right? And the next one is the proper motion. Proper motion is the other one that we can measure, right? You can measure the radial velocity, and then you can measure the proper motion. Proper motion is the angular change from here to here for a particular star, right? So that can be measured. So remember, in practically, this is what you can measure: the radial velocity and the proper motion, right? Proper motion is normally indicated as mu, and it is kind of, number of arc seconds or arc minutes. Normally, it should be arc seconds, right? Not that much. And then if we can measure the distance from here to here, from parallax method or something like that, then using this proper motion and the distance from here to here, you can calculate transverse velocity, right? That's what I have mentioned before. So when you know the radial velocity and the transverse velocity, then you can calculate the resultant of those two vectors to find the space velocity. So that's how you do the calculation, right? And basically I have summarized it here. Just go through and read it. Right, so I have mentioned it here as well. To know the true space velocity of a star, that is total speed and the direction in which it is moving through the space relative to the sun, we must know its radial velocity, proper motion, and distance. A star's space velocity can also over time cause its distance from the sun to change significantly, right? You can see that from the space velocity, if it has a space velocity, it changes position, right? And this will affect to change the distance of that particular star from our sun, right? And this effect will come after several 100,000 years, right? Now, one example is that, that if a star is going away from us, its brightness for us will decrease a little by little, right? As a result of that, today the Sirius in the constellation Canis Major is the brightest star in the sky. If you go outside, the Sirius is the brightest star. But because of these movements of the stars on the sky, 100,000 years ago, there is a star called Canopus, right, in the constellation Carina, which was the brightest one, right? So remember that the Sirius will not be the brightest star on the sky forever, right? So it is the brightest star now, but it was not the brightest star around 100,000 years ago. And similarly, little over 200,000 years from now, which means in future, Sirius will have moved away and faded somewhat, and the Vega will become the brightest star. You can see that at different eras of the universe, different stars will get this position, right, as the brightest star. Now, this came as a result of these motions of stars, right? Right. And that's the story of moving of the movements of the stars into different directions. And apart from that, when you talk about the stellar motion, the stars can rotate itself as well, right? Now, this rotation of the stars and the rotational speeds can be also measured using Doppler effect, right? So Doppler effect can be used to measure how fast the star rotates, right? Now, if you have an object rotating, what happens is one of its sides, these stars are very huge objects, right? So one of the sides will be moving away from us and the other side will move towards us, right? If a star rotates. And so because of the Doppler effect, what happens is when the side that is moving away from us will be red shifted, and the side that moves towards us will be blue shifted, right? So that's what normally happens. Now, if a star is rotating rapidly, then what happens is this spread, that one side is moving away from us and the other side is moving towards us. the spread of this Doppler sheet will be quite broad, and this is and you can see that now that the broadness of the spectral lines will give you an idea about the speed of the rotation, right? So that's how these two are connected, and this particular effect is called as line broadening. Right? Now these are the important things that I have highlighted here. Make sure that you get the idea, right? So if I tell line broadening, you should know what that means, right? Because these words you may not have seen before in other subjects, and this amount of broadening, how broad is the line, will be able to tell us the speed, right, at which the star rotates. Now, from a diagram, we can understand this very clearly. Here is a star that does not rotate, and it has a line right here in the spectrum, and that means that the intensity has dropped there. Now, when the star starts to rotate, this side go away from us, this side come towards us, and as a result of that, this particular line will become broader, right? And as a result, this dip has become broader from here to here. The width has increased, right? Now this is what we call as line broadening. Right? So you can clearly understand that if the rotation speed increases, this will be much broader. So this is why you can use this effect called line broadening to get an idea about the rotation speed of a star, right? Right. Now these are two stars. Altair is one of the bright stars in the sky, and our own sun. The rotation period of Altair is 6.5 hours, while our sun rotates 24. Rotation period is 24 to 30 days. Right, so that's about stellar motion of the stars and rotating stars. And the next one that I would like to talk is the binary star systems, right? Now, this is something actually an important or interesting topic, and I know that some of you are actually doing some research in this area as well. The binary star systems, or we call this as double star systems. Now, most of the stars that we see are actually parts of multiple star systems revolving around the common center of mass. Right? We don't know it, but when we are looking at the stars, most of them are actually multiple star systems, which means there may be one or two, maybe even more than two stars involved in these star systems, right? And these are normally called as, if there are two stars in the system, we call those as binary star systems. And in astronomy, we divide these binary star systems into different, 2 or 3 different types of binary star systems. The first one is called visual binaries, right? Visual binaries means it's straightforward. You just go to a telescope and look at a particular point, and you can clearly see that there are two stars close by, right? And those are called, visual binaries, because visually you can see that. Right? Visually means through a telescope. Now, these are normally sufficiently close to the Earth and can be seen two stars individually from the telescope. Right? Now, these type of stars are called visual binaries, right? But there are other types of binaries as well. The second type is called astrometric binaries, right? So these type of binaries, you cannot see two stars, but you can detection of an unseen companion of a binary star by gravitational influence on the primary star, right? So when you look at that particular star system, you cannot see two stars. However, you can measure the gravitational influence on the primary star, right? Now, this method is very useful when these binary systems are too far away and stars are too close to one star. Right? And also, if there are two stars, that one is much brighter than the other one, then that is also used, and this method is also useful, right? So you can just use the Kepler's law to calculate the mass of a binary system for these type of stars, right? Right. The third one is spectroscopic binaries, which means when you look at the sky, you don't see two stars. The system appears as a one star. But if you look at the spectroscopy, you can clearly see that there should be two stars, right? And these type of binary star systems are called spectroscopic binary systems. And here is how you figure that out. Now, there are two stars, right? And one is rotating around the other. And the star A is now at this particular diagram at number 1, the star A is coming towards you and the star B is moving away from, right? And then you should see the two lines like that. And for the number 2, the star B is moving this direction and the star A is moving this direction. Now both the stars are moving perpendicular to us. So which means you would not see any difference. And you will see something like this, right? And then when star B come to this position, the B is now moving towards us. Now A is moving away. So which means the B will be here, A will be here. Now these two are changed now compared to this one, right? Again, the other position is when B and A are perpendicular to each other, perpendicular to us as well, which means then you will have one line, right? So looking at this spectrum, you can decide, okay, there are two stars. So make sure that you understand it. So I have some text here for you to understand it when you read through it. And here is how the radial velocities looks like in the spectroscopic binary system. It is actually not hard to understand. You can see that when the one has what are the velocities from this graph, right? Just a plot of radial velocities. Right, so the fourth type of binary star system is eclipsing binaries, right? So as the name suggests, the eclipse means one will be covered by the other star, right? Now, if two stars orient such that one star can pass the other star, then they are called as eclipsing binaries, right? So one star will go in front of the other, right? Now, accurate sizes of large number of stars come from these measurement from the eclipsing binary star systems. And here is a nice example and drawing that shows it. There are two stars. Here is the one right at the middle. You can see it's a large star, but its color is red, right? So just take the same color that I have here. And there is a small star that goes around this large star. The color of the star is blue. And here is the light curve. Now, if I have not introduced you light curves before, the light curve means how the brightness change over the time for a star system, right? Light curves are also used in other fields in astronomy, but here we are looking at the combined light curve of these two stars. Now, if I explain this, these numbers that I have put here, number 1 right here. So that is when you have the two stars separately, which means if you look at these two star system, the star system from the Earth, you can see the large star at the center and the small star both at the same time, right? The idea is the light coming from the largest star and the smallest star both, and you will observe both the total amount of light from both the stars. So at this particular position, you will get the maximum light due to that reason, right? And then you can see that at position number 2, the smaller star has gone behind the largest star. right? So the largest star is the red one right here. And at position number 2, the small blue star is behind, right? So which means, of course, when you look from Earth, you can only see the light coming from this largest star, right? It has completely blocked this smallest star, right? So what that means is you should see a drop of light, right? So that's what this particular curve means at point 2. So it drops the light at position up to position 2 because there is a drop of the light. That basically the light from the smaller star you cannot detect, right? And when it comes to the position 3 right here, once again, you can see the light from this star plus the largest star. Right? Both the stars are separated, right? One has not covered by the other one. Because of that, when you look from the Earth, you will see the total light coming from the blue star and also this red giant star, right? Which means again you will get the total amount of light. So which means it will be same as position 1 that we talked. So therefore, the amount of brightness will increase for the system, and for the position 3, the light will be like this. And then you can see that when the small blue star comes to the front right here at position 4, now make sure that you understand the small part of this large star is blocked by the small blue star, right? So which means when you look from here, from Earth, you will see both the stars, but you will not see the complete red star because this small blue star has covered the small part of this large red star, right? Because of that, when you look from the Earth, there should be a small loss of light, and that is why you get a dip like this for the light curve, right? So I expect that you should be able to understand these type of things, right? These are just, you have to think how it works. Now you should have a question now in your mind, why this number 2, the drop at number 2 is larger compared to number 4. Is there anyone who can answer for this one? Just from the knowledge that you have about stars now, why this number 2 drop is larger compared to number 4? So please talk. It seems to me that most of us may be sleeping, right? So is that I'm only talking and you are not listening? Anybody knows why that happens? I got one answer. Who else would like to answer? So if you are not answering, I will leave that to you, right? This is a very simple thing that you just need to think about. What are the factors that affect the brightness of a star? Right? So I have one answer from Sajini that the brightness of the big star is larger compared to the smaller one. And so the small star's brightness can be neglected. But Sajini, if this is the case, if you can neglect the small star's brightness, then at position 2, you can see that the small star is completely behind, right? So you can only see the light from the largest star. So if you don't need to consider about the light from the smaller star, then you should not expect a huge drop like this, right? So what you need to logically think, what you need to understand here is the light drop a considerable amount when the small star is covered by the large star, right? Now, this is why I want you to think about this, right? This is not something that only related to astronomy. This is about the thinking process that you should practice to logically think what happens here. Right. So since you are not answering, what I am going to do is I will stop the lecture now, and I'm going to post this as an assignment for you. So everyone has, I want a written answer from everyone, right? So that's what I am going to do. So I can check how you can write an answer for this one, right? You probably need to, okay, the question is explain this light curve, right? Why you have a dip and number 2 compared to number 4, right? So this is, it should be interesting. Right, so I'm going to post it. So you probably have to answer for that by Friday. So I will take the answers, right? Right, then if you do not, anybody have any questions then up to here? I have just 2 slides to finish here, but I will do that on the next day. It's almost 9:30 now. Sajini, I think you can think a bit more. So I appreciate your answer, by the way, but just think about.
Determine about the radius of these stars.
Yes, you can do that, because I mean, you don't have to have an exact number. What you it's clear, you know, the largest star has a larger radius, right? Small star has a smaller radius. I guess this is enough to get an idea about, you know, you don't need to plug the numbers, right? I think you are in the right track to think about this. Yes, you have to consider the radius, it is true, and then the color represents something else, right? So that's actually temperature. And remember, we talked about these things before as well, the temperature
So
and the
then I
color.
think light blocking is somewhat proportional to the size of the planet.
That's not exactly true, because right now, since you have given the answer, let me discuss about this. Now, there are 2 things that affect for the brightness of a star, right? We have discussed. That's the radius, which means the size of the star, and the second one is what? Temperature, right? So what you need to figure out is which one is more important, right? That is what you have to now what you have decided here is the size is more important. So that is questionable, which, I mean, just think about the equation for the luminosity, right? So that is L equal 4 pi and surface area times the 4th power of the temperature, right? And you can see that the size and the temperature both matters for the luminosity of a star. And the size, you have to decide which one is more important, right? Either the size or the temperature. So what normally, if you think about these spherical shapes, the area is 4 pi r squared. So that means this radius of square of the radius comes into play. But then you have the 4th power of the temperature, right? So what you have to decide is what is more effective, right? Basically, these 2 stars are actually, the larger one is cool large star, the smaller one is a smaller hot star, right? So think about it in that way. I guess it's better that you write an answer for this one, but probably I will just give you this as a small question in a tutorial. right? So if anybody else need to ask anything about this, so Sajini, is it clear now? I think you got the idea, right? You can
Yes, sir.
think about it. Yes, yes. Right. For others, think about that and come up with an answer, right? So, right. So, thank you for joining today. We will meet again on next Friday in the usual time that we had, like Friday 5 p.m. in the evening. But if anybody else need to change the time, please let me know, right? This is like completely, we can discuss and change it if anybody have a difficulty, right? Anytime if you have like any different plans, if you need to change it a bit for a different time, it's completely fine, right? So just discuss with me, we can just discuss and change it at any time, right? Right, then I'm going to stop the lecture since anyway, if you do not have any questions. So thank you for joining today. So we will meet again on this Friday.